Welcome to Calc Chats 12. Today we're going to be talking about differentiability and continuity. So continuity is defined as a function, that a function is continuous on an interval if and only if it is continuous at every point on its interval. So this is a pretty basic definition. All it really means is that when I have a function, if I can draw it without picking up my pencil, it's continuous. An example of a discontinuous function would be if I drew it and then I had a hole and then I started up again. I can't draw that in one motion. I have to stop and then start again, so this one is not continuous. But if I can draw it with my pencil without picking up, it's continuous. So with that continuity comes the intermediate value theorem. So this theorem is kind of long. Basically, it states that if we have a function that's continuous on a closed interval, then that function takes on every value between the y values. So when we're looking at, let's say, this function right here, I'm given a and b, and this value is f of a, and up here this value is f of b. So basically all it's saying is if I have this continuous function, then at some point along this line, I'm going to hit every point between f of a and f of b. So if this was, let's say, 2 and 5, I would hit 2.1 at some point, I'd hit 3 at some point, I'd hit 4.9 at some point, but I would hit all of the values between 2 and 5. So with continuity, we're going to talk about differentiability. And first, I want to talk about how a derivative might fail to exist. And so we kind of have 4 different types of possibilities for the derivative not existing at a point. So if we're given a corner, so if I have the absolute value, that's a classic example. I just have a corner. The derivative doesn't exist at that point because if we take the derivative closer and closer to 0, they're not going to match up, and so that derivative doesn't exist. Another example is a vertical tangent, so y equals the cube root of x. And so this one has a vertical tangent at 0. So we can basically draw a straight line. And obviously, we can't find the derivative of a vertical line because that would be 1 over 0, and that doesn't exist. So that's another example. A cusp, this might be a new vocab word. A cusp is kind of like a corner, but it almost curves in. So our cusp would look like this. So it kind of looks like, you know, the birds you would draw when you were a kid flying off into the sunset. But a cusp, it just comes together and it's kind of like arcs on both sides. And so a function that looks like this would be y equals x to the 2/3. So that forms a cusp. And then just regular step discontinuities, jump discontinuities. So a step function would be a good example. A piecewise function also. So if I have a discontinuity there and then I come back up, it's obviously not continuous, so I can't find the derivative of that point. The reason we're talking about this is because differentiability implies continuity. So if I can take the derivative at that point, that means it is continuous at that point. However, the converse is not true. So continuity doesn't always imply differentiability. And we can see that in our corner, in our vertical tangent, and our cusp examples. Those are all continuous functions, but they're not differentiable. And so we know that if we do have a differentiable function, that it has to be continuous at that specific point. So we're going to use this idea with the intermediate value theorem. So if we're given function like we were with the regular intermediate value theorem. This one is just for derivatives. So we have a, b, f of a, and f of b. So this states that if I have f which is differentiable, and at this point we can also assume that this means it is continuous as well. So if it's differentiable, it's continuous. So if I have f that's differentiable, then f prime takes on every value between f prime of a and f prime of b. So basically what this is saying is when I look at the derivatives at f of a and f of b, so we can say this derivative might be 1, the slope looks like it's 1, and then this derivative might be 2. I can find a derivative anywhere from 1 to 2 on any point on that interval. And in order for us to use the intermediate value theorem, we have to have a continuous and a differentiable function. I know that I keep repeating myself, I keep saying that, but this is going to come in play when we're using the intermediate value theorem, looking at functions, deciding if it's continuous or differentiable. We need to know that it is continuous, it is differentiable to use the intermediate value theorem. We can't use it for other functions. And so last thing I want to quick talk about before this episode is done is the derivative at a point x equals a. So this is a new notation. We've been dealing with the limit as h approaches 0, f of x plus h minus f of x all over h. That's been kind of the definition of the derivative, and now this is just another way to view the derivative. And so we'll have to be able to identify functions set up in this format. So let's look at a quick example of using this different notation. So I'm given the function f of x equals the square root of x plus 1. And I want to find the derivative at a equals 3. So I know from my previous slide that definition for us is f prime a equals the limit as x approaches a of f of x minus f of a all over x minus a. For this function in particular, this is going to look like f prime of 3 equals the limit as x approaches 3 of f of x is just x square root of x plus 1 minus f of a. That's square root of 3 plus 1 all over x minus 3. So now I'm going to just kind of rewrite this. X approaches 3, root x plus 1 minus 3 plus 1 is 4, and so the square root of 4 gives me 2, and then x minus 3. So I want to evaluate this limit, but I can't plug in 3 yet because that would give me 0 in the denominator. So what I'm going to do is I'm going to multiply by the conjugate of this root. So x plus 1 plus 2, x plus 1 plus 2. And I basically want to rationalize my numerator. So then f prime of 3 equals limit as x approaches 3. Square root of x plus 1 times the square root of x plus 1 is just x plus 1. And then minus 2 root x plus 1 plus 2 root x plus 1, and then minus 4. All over, and you never want to multiply your, whenever you're trying to rationalize something, you don't want to multiply the things that don't cancel out. So this x minus 3 times root x plus 1 plus 2, I don't want to multiply those out yet because I want to see what's happening in the numerator first. So f prime of 3 equals limit as x approaches 3, and yes, I do have to keep rewriting this. These two cancel out, so I'm left with x plus 1 minus 4, and that gets me x minus 3 all over x minus 3 times root x plus 1 plus 2. And the reason, like I said, we don't want to multiply anything out yet is because those x plus 3's cancel out. So now what I'm left with is 1 over root x plus 1 plus 2. Now I can plug in the 3. So I'm looking at f prime of 3 is equal to 1 over square root 3 plus 1 plus 2. And so that limit is equal to 1 over 4. So this video kind of delved into more definitions than it did problems. So we're going to kind of use the definitions that we covered to solve even more problems about derivatives. So please come to class with any questions that you have about this video, intermediate value theorem, and please like and subscribe. Thanks for watching.